Hello everyone and welcome to my presentation for Project 2 Statics by me, Guerra. And let's begin. The objective for this project is to create a Mars lander that will resist a 1 meter high fall. Design the lander to resist higher altitudes and hopefully go over 2 meters. Land safely and calculate the forces applied to the Mars lander, which is going to be the forces such as velocity and per leg to see if it's going to resist or it's going to fail this test. These are going to be the main ones, or some of the few designs of Mars landers that were successful in landing on the Mars surface, which are going to be the Inside, Phoenix, and the Viking one. I got different ideas on how to create my sketches out of these three. These are gonna be my three main sketches. As you guys can see. My first one was really basic, just having a round body and 3 legs with the egg in the center. Then I had to modify it and make it stronger, and I did that by making it kind of square, or triangular with 4 legs, and I just kept the egg in the center for protection. And the final one was changing the body to a square one and going back to those 3 leg designs with a parachute to slow down the fall. My materials were hot glue, a glue gun, spaghetti, plastic bag, string, cardboard, and the extra which is pilot Roger Rhodes. The images you guys can see my final product of the Mars lander with the pilot, the astronaut in the center, the plastic bag that was tied up with the strings to the lander. Different angles, and this is without the bag for a better angles. The weight was 442 grams. Dimensions were 6 by 4 by 5. The cardboard box was the landing pad, which is 300 meters by 300 meters, which was pretty much made just to demonstrate that the lander did in fact fit inside those dimensions. Okay, and I did upload the videos, and these are the links for test 1 and test 2, 1 meter and 2 meter high drop. And let's go ahead and take a look to see how it went. This is gonna be 1 meter, and let's take a look. Try number 2, 3, 2, 1. And it seems that he did survive. Okay, for the 1 meter, and the astronaut was able to survive, so we went to a 2 meter fall. And let's take a look how that went. 2 meter drop in 5, 4, 3, 2, 1. Two meters fall. Success. For the 2 meters, I wasn't able to go up to 3 meters since the lander did receive a lot of damage, making it almost impossible to reuse. Let's go ahead and continue with the presentation. Okay, for my velocity calculations, as you guys can see, The mass was 442 grams, gravity 9.8 meters per second squared. Initial velocity is zero, final velocity is unknown. So when I had to use kinematics formulas to find the final velocity, um, in the 1 meter drop and the 2 meter drop, for the 1 meter drop, I ended up getting 4.43 meters per second for the final velocity, and for 2 meters, I got a 6.26 meters per second. So it's not that bad. But it at the end, the Mars lander was successful as to saving the astronaut from crashing. And let's continue with the analytical calculation. For this, performance was drop height divided by the weight, which I went ahead and did the math and I got a 0.0045. Now my theory body diagram with my knowns, and by doing the math of equations of equilibrium, I went ahead and found the um, force that each of the legs was um, withstanding, which was 4.125 newtons. And for my conclusion, the astronaut did survive the 1 and 2 meter high drop. Velocity for 1 meter, 4.43 meters per second. For 2 meters was 6.26 meters per second. And the force applied per leg was 4.125 newtons. And I would consider this to be a success since our astronaut Roger Rhodes did survive. And thank you for watching.